Hello, welcome in the 15th lecture of two-phase flow and heat transfer. Today we will be discussing about smoothed particle hydrodynamics. This is a Lagrangian methodology. So, let us see at the end of this lecture we will be understanding the algorithm for solving multiphase flow in SPH. We will be doing a practice of this type of particle based methodology simulation using a freeware. So, we will be installing the freeware, we will be showing you how to set the model parameter, how to run the case study and finally, how to obtain the result and analyze those. Based on the present experience, you can start your own simulation for two phase flow using smoothed particle hydrodynamics. So, let us first go to the equations what we follow in smoothed particle hydrodynamics. As I have mentioned, smoothed particle hydrodynamics is one Lagrangian type of method. So, obviously, we have to deal with Lagrangian equations. Okay. So, in Lagrangian framework, if we try to write down the Navier-Stokes equation and energy equations, the equations will look like this. So, continuity equation will be transforming into d rho dt is equals to minus rho del v. Okay. Momentum equation will be transforming to dv dt equals to minus 1 by rho del v. Okay. And then energy equation will be transforming to dE dt equals to minus 1 by rho p del v minus of 1 by rho into del q, q is the heat transfer over here due to conduction. So, q is equals to k into delta T. Okay. So, these equations are coming from fluid mechanics. So, I am not going to elaborate discussion of these equations. So, let us see that how using smoothed particle hydrodynamics we can tackle this type of equation especially for two phase flow. Okay. So, in smoothed particle hydrodynamics the domain is actually discretized using Lagrangian particles. So, this is a new concept in our common computational fluid dynamics analysis. We have seen the domain is discretized into either volume or element or nodes in finite difference. Okay. So, here in case of this smoothed particle hydrodynamics the domain is actually consisting arbitrarily distributed particles. So, here I have shown you one typical example. Let us say this is your domain and in this you are having arbitrarily distributed particles. Okay. The particles are always doing some sort of interactions amongst themselves. What type of interaction depending on the governing equation we need to decide. Apart from that we need to also find out that which particles are actually influencing a single particle of interest. Let us say here this black particle is our particle of interest. So, we can draw always a circle in 2 dimensional or a sphere in 3 dimension having a radius, that radius let us say is h. This radius is called smoothing radius or smoothing zone. Okay. And then you see in this domain, circular domain, the particles which are falling inside those actually will be influencing the particle of interest, here the black particle. Okay. So, this H is very important in case of your smoothed particle hydrodynamic simulation. If you give a very large H, then all the particles will be coming into picture, and if you give smaller one, then you have to you will be finding out that your results are not coming into the converged simulation. Okay. So, choice of H is very important. Okay. Next, why this Lagrangian field is chosen? Let us see. Actually, we will be trying to convert the differential equations into algebraic equation, which is the basic essence of computational fluid dynamics. So, what we will be doing over here, let us say you have a field which is F. Okay. So, defined at a particular position I. So, let us say this is your ith position. So, the position can be known as Ri, let us say the location of this one is known as Ri. So, if Ri is the field at ith position, so that can be written as summation of mass of all other neighboring particles coming under the influence of this particle. So, all these shaded particles are having denomination as jth particle. So, mass of jth particle multiplied by field of those neighboring jth particles divided by rho j, density of those jth particle, multiplied by some smoothing function W. The smoothing function is actually a parameter, it depends on a parameter which is nothing but the mutual distance between the particle of interest and the neighboring particle. So, Ri minus Rj, right. So, here you see if you have a field variable. So, the field variable we have found out depending on the values of the field variable of the neighboring particles. Okay. So, neighboring particle j will be very important, and based on all the j's or neighbors we have to sum it up. Okay. Now, this field variable can be anything, it can start from rho density, it can be velocity, it can be energy, it can be pressure, it can be heat flux, anything. Okay. So, in our equations, previous equations, we have shown that we are having density, velocity and your temperature. Here it can be some more quantity also. Okay. Next, why this kind of approximation is necessary? By the way, this approximation is called a kernel approximation, and here whatever smoothing function we use, that is actually called a kernel. Okay. Now, why this type of kernel approximation is important? You see, if we are interested to find out the Fri, inside this you see, apart from this Ri minus Rj, that means this smoothing function, we do not have anywhere the dependence of I. Okay. So, if I try to discretize or if I try to differentiate this variable with the value of Ri, then I will be finding out this term will be acting Mj Fj by rho j, this will be acting as constant. Okay, because the Ri is nowhere present over there. So, only Ri is present in the smoothing function. So, only the differentiation will be coming on the smoothing function. So, here I have shown you that one. Let us say the first derivative you want to make with respect to let us say Ri, okay, for over this Fri. So, you will be finding out that this term, okay, whatever we are having, that will be acting Mj into Fj by rho j, that will be acting as constant. So, that can come out, and only the differentiation will be acting on the smoothing function, okay, Wrij, okay, Wri minus Wrj. Okay. So, that differentiation only comes over this Wij. Okay. So, this is a very important advantage. Why? Because the field variables you need not to differentiate, only the differentiation of smoothing function which we are predefining or we are presetting, that one will be actually working for us. Okay. So, here the simulation actually boils down into bookkeeping of all the particles informations, okay, and the differentiation of the smoothing function will do your task. Discretization in a proper fashion is not necessary. Okay. So, you can go for higher order derivatives also. So, nth order derivative will be giving you over here nth order derivative of the smoothing function, rest things will be coming out as constant in the equations. Okay. So, let us see that how this concept can be used for solving momentum equation and continuity equation. So, what first we will be defining? We will be first defining the local density of the particle. Okay. So, local density, let us say this F, whatever I have talked about, the field variable is density. Okay. So, F Ri is nothing but your rho Ri or rho I. So, F we are first considering as density. So, if we try to write down what is Fi or rho I, okay, using the previous definition as I have shown you over here. So, sorry here. So, then we will be finding out this rho I will be equals to Mj into rho j by rho j into W of Ri minus Rj. So, rho j can be cancelled out. So, finally, we will be getting that rho I is nothing but summation of Mj into Wj, rho j is cancelling out over here. Okay. Now, this Wij is nothing but the kernel function. Okay. So, density of a particle can be defined by the summation of Mj into Wij. Okay. Now, if we try to write down the continuity equation, you know that continuity equation already I have shown you, d rho dt is equals to minus of rho into delta v, which can be once again simplified as delta of v rho minus of v into delta rho by using differentiation by parts formulations. And here you see the right hand side, we will be writing here, we are having the derivative of some field variable. So, field variable is v into rho. So, we can write down Mj into Vj rho j by rho j. So, rho j cancels out, and then differentiation of the W, because we had first derivative of v into rho. So, this will turn out to be first derivative of the Wij. Okay. Next term over here you see we are having only del rho. So, Vi will be remaining outside because this we are writing for ith particle. So, for del rho we will be writing down already I have shown what is rho I. So, for del rho I it will be nothing but mj into del of wij because this mj is not dependent on the ith particle. Okay. So, our continuity equation comes out to be d rho I by dt is equals to, here you see here we are having Vi and here we are having Vj. So, I can write down this is nothing but, and we are having minus sign over here. So, we can write down this is nothing but Vij. So, finally, I get d rho I dt is equals to minus of summation of mj Vij and then del of wij. Okay. Similarly, momentum equation can be written. So, I am not describing the full procedure over here, but analogy will be same. If you are having differentiation, the differentiation can go to the smoothing function and the variable can remain outside. So, here in a similar fashion you see this is the momentum equation. So, left hand side we have kept as usual because with this we will be finding out the next time instance velocity. So, dvi dt. In the right hand side you see this is coming from the pressure term. So, we had del p. So, del p can be written as pi rho I square summation of mj del of wij. So, you see derivative once again coming to the smoothing function. And here also what we can do as we are having dependence on both the particles, that means your pi and pj. So, we can write down this is on pj and here we have taken this one inside. So, this is nothing but in your momentum equation if you see here we are having del v. So, del v can be written as pi is going outside. So, this is nothing but your del v over here and this is del vp. Okay. So, p is taken inside using by parts. Okay. Now, for finding out your next positions value, so we have to find out the force. So, what we will be doing, this Fi is nothing but mi into dvi dt. Dvi dt already I have found out over here. So, Fi will become summation of mi mj and then within bracket pi by rho I square plus pj by rho j square and sole derivative will be remaining on w. Okay. Similarly, energy equation can be written. So, this is your energy equation part. In the left hand side we are having the temporal variation of the energy and in the right hand side we are having minus half summation of mi mj pi by rho I square plus pj by rho j square into Vij and then derivative over the w. Okay. Minus this one is for the conduction term. Okay. So, we are having Ki plus Kj okay, by Rij multiplied by Ti minus Tj Rij into derivative of Wij. Okay. So, this is momentum equation, final momentum equation, this is final energy equation comes out to be. One important thing here we need to look is that nowhere the derivative of field variable is there. So, only the derivative is over the smoothing function. Okay. Now, we know that what we have done in this methodology, that the domain we have discretized in particles. So, now those particles will be breaking the continuum nature of the fluid. So, to gain back the continuum nature of the fluid, what we need to do? We need to give some artificial viscosity from outside. Okay. So, here we are giving the artificial viscosity using von Neumann-Richtmur artificial velocity. So, you see over here if you remember the momentum equation earlier, we had Fi is equals to minus of summation of mi mj and then pi by rho I square plus pj by rho j square. Here we are adding this extra term pi ij based on the von Neumann-Richtmur artificial viscosity. Okay. And this term was earlier also there, derivative of the smoothing function. Right. So, this is the proposition of von Neumann and Richtmur. They said that this will be the artificial viscosity we can add to gain back the continuum nature. Okay. Similarly, in the energy equation you see energy equation also we had this pressure terms. Okay. So, there we can add this pi ij. Okay. Earlier this was with pi ij equals to 0 without this von Neumann and Richtmur artificial viscosity. Okay. So, here we can add also pi ij over here. right. Now, what is this pi ij? Here this von Neumann and Richmond they proposed pi ij can be written as minus of alpha into h. Okay. Remember, this h is nothing but your smoothing length multiplied by Ci plus Cj into Vij Rij divided by rho I plus rho j Rij square plus epsilon into h square. Okay. Now, what are these factors? Ci and Cj we can understand, those are the sound speeds of ith and jth particle. Alpha is dimensionless factor and it controls the dissipation strength. So, it depends on the fluids which parameter we are taking. Okay. So, depending on fluids the alpha needs to be tuned. Okay. So, this is a tuning factor which we are having to control the viscosity. Okay. So, obviously, the particulate nature will not be gaining back the continuum nature for all the fluids in with the same value of alpha. Okay. And epsilon, which is nothing but 0.01, it avoids singularity between the close particles, because if the particles are coming very close to each other, they will be once again acting as continuum. So, this alpha sigma is actually given for this one. Okay. So, once we know that what are these tuning factors, okay, alpha and sigma, alpha and epsilon, and Cij's are the particle sound speeds, okay, all these are known, then you can find out what is pi ij and you can put it over here for the I and jth particle, and you can evaluate the values of your Fi and subsequently what is your energy in the next section, okay, next time step. So, in this way we will be continuing, but the problem will be becoming little difficult whenever we are having two phase, because in two phase we know there is some interface, and across the interface we will be having some surface tension force applicable. So, what we do to take care of that one in this space simulations, we actually denote the particles with some color. Okay. So, these colors are dependent on the phases. So, let us say we are having two phases, gaseous phase and liquid phase. So, for gaseous phase we give one color and for the liquid we give the other color. Here I have shown you a typical situation. Let us say this is gaseous phase, at the top of this one explained by red colored particles, and over here this is the liquid phase explained by the blue colored particle. And so, definitely the interface will be lying somewhere over here, which is differentiating between red and blue colored particles. Okay. So, what we do in numerical simulation of SPH also, along with the other properties like rho I and Vi and Ei, we define another property called Ci, okay, which is called the color. So, what we do, we give the color to the liquids as 1 and we give the colors to the gas as 0. Okay. Now, once we know the colors of the fluids, what we can do, we can find out what is the normal direction of the interface, because always we know the change of color, if we try to find out the gradient of that one with respect to space, that will be giving us the normal direction of the interface. So, n is nothing but del of Cs, where Cs is the color field. Okay. So, once we know the value of n, then easily we can find out the surface tension force. Okay. Surface tension force will be only applicable in the zone of the interface. So, what we do, we use delta Dirac function, okay, to apply that surface tension force. So, we can write down surface tension force Fs will be actually Fs, which is the surface tension force multiplied by this delta Dirac function delta S. That means, this delta Dirac function is only applicable near the interface. That means, delta S is equals to 1 at the interface and elsewhere it is 0. Okay. So, what is this nature of Fs? So, Fs can be written as minus sigma, where sigma is the surface tension force, into delta square Cs, okay, n by n bar. So, n by n bar is giving you the unit vector of the normal direction. Okay. Now, how to get once again these derivatives of this Cs double derivative and single derivative over here? I have already shown you how to perform the derivatives on a field using f. So, here you will be doing the same approximations over Cs. Okay. So, once I know all the particles Cs, we can find out its first derivative and second derivative using Kernel approximation. Okay. So, in that way the capital Fs will be calculated, and with each particle that portion will be added. Okay. Here I have shown you what is small fi. So, this small fi will be coming into picture along with this capital Fs to find out what is the force on each particle, right. So, in this way we go for two phase simulation. let me show you the algorithm for time progress. So, time advancement. So, the method we follow is actually Varlet algorithm. So, what is the algorithm? Let us say at present time step, which is tth time step, we know all the variables, that means starting from v, rho and e we know. Okay. So, how to proceed further? So, using VIT which is the velocity at tth time level, we find out some intermediate time level, which is nothing but t plus del t by 2, okay, some half time level we can say. Okay. So, that we find out using Vi t plus del t by 2 is equals to Vi t plus del t by 2 mi Fit. Okay. So, you see over here this Fit is nothing but the force, okay, force on the ith particle, okay, at tth time step. So, in the left hand side, in the right hand side, everything is known to me. So, mass of each particle, velocity at tth time and force at tth time we know, and delta t we will be choosing. So, time step we will be choosing. So, depending on this we will be finding out the velocity at some intermediate time step t plus del t by 2. We can update this one, or we can find out a new variable which is nothing but Vi bar. Remember, this Vi bar is not V t plus delta t. So, what we are finding out, some new variable we are defining in Varlet algorithm. So, Vi bar at t plus delta t we find out based on the full time step now. Previous equation I have showed you for the half time step t plus delta t by 2, here we go for the full time step. So, you remember, you see the equation looks like similar, but only thing is that here we had delta t by 2, here we had only delta t, because this is for the full time step. So, we have found out two V's, one is Vi at half time step, another one is Vi bar at full time step. Okay. Similarly, we can obtain other variables like rho I and Ei for half time step. So, these equations will be similar to the first equation whatever I have showed, dependent on the tth time step values and corresponding delta t values. Okay. Okay, fine. Then we can also update the value of r, which is the position variable. So, Ri t plus delta t is equals to Ri plus delta t. So, this time we require a velocity, this velocity we will be using as the half time step velocity. So, V t plus delta t by 2, here you see we have multiplied Vi t plus delta t by 2. So, this Ri t plus delta t is actually found out by half time step. Okay. Next step, second step, after finding out all these variables at t plus delta t by 2th time step and a pseudo velocity at t plus delta th time step, we will be going for calculation of actual value of force, energy and your density change. Okay. So, remember these are dot quantities. So, with respect to time how much it is changing, that we are trying to find out. Okay. Now, this we can find out by putting the value of Vi t plus delta t. So, Vi bar t plus delta t in your continuity, momentum and energy equations. If you remember, in continuity, momentum and energy equations we are having, they are time derivatives in the left hand side. Okay. So, all these quantities can be found out using your continuity, momentum, momentum energy and continuity equations respectively. Okay. And using V bar t plus delta t in the right hand sides. Okay. So, once we find out these updated values of Fi, Ei dot and rho dot, we will be updating the values of actual rho, Ei and Vi using the half time steps values and the rates. Okay. You see rho I t plus delta t is equals to rho I t plus delta t by 2 plus delta t by 2 d rho I dt, which is nothing but rho I dot at t plus delta t, which we have found out in the second step. Okay. Similarly, Ei can be written and Vi can be also written. So, once we get the new time steps, density, energy and velocity values, we will be forwarding march for the Ti plus 2 delta t. Okay. So, in this way Varlet algorithm works. Okay. Next, let us see what are the freeware available to solve smoothed particle hydrodynamics problems. Okay. Usually we are having many open source software, but here I will be giving you names as LAMPS SPH multiphase, S physics, fluid V.3. So, these are different software where SPH is actually included as case. Okay. But today I will be showing you one simulation for a case study using LAMMPS SPH multiphase. Okay. First let me see what we require to install this LAMMPS SPH multiphase. So, you require a Unix platform, okay. Also you require a working library of C++, GCC or G++, okay. And what are the steps for installing the LAMMPS SPH multiphase? First you need to download it from the software package ID I have given over here, okay. And then you have to extract the package and copy it in the home directory. How to extract already I have shown you, so you can follow that step. Okay. Then you have to go to that folder where you have extracted, okay. More or less the folder will be taking this name, LAMMPS SPH multiphase surface tension clean. Okay. So, you have to, so the main folder will be LAMMPS SPH multiphase surface tension, okay. LAMMPS SPH multiphase. In that you will be finding out one folder called surface tension and another folder called clean. Okay. So, you enter in that clean folder by doing cd. So, already I have shown you how to do that, and then open this readme.org. Okay. Then in that you type the following command in terminal for installing the packages. Okay. So, usually I have shown here all these commands based on Ubuntu 12.04.5 version. Okay. So, what are the commands you need to give? So, major commands are this one. So, you have to install these packages git, OpenMPI dev, OpenMPI bin and libjpeg dev. So, these are necessary for running of LAMMPS SPH multiphase. Okay. So, you need to do sudo apt-get install and the package name for all these packages. Then once this git is properly installed, you can git clone from the library where this SPH multiphase is installed. The library is actually in slithonov / LAMMPS SPH multiphase. Okay. So, the address is written over here. So, from that you can clone down using git. Okay, then you can go to that folder where it has been actually downloaded. That folder will be LAMMPS SPH src. So, that is the source folder where all the codes are saved. You can go over there and write down make yes user SPH. So, that enables all the SPH packages to run, and you can use your SPH codes over here. Then you have to install the package using make linux cc mpicc. So, this is one C++ directory, and then you have to link it with mpicc and cc flags -2 -g fft_lib equals to -lm. Okay. So, you give this command, your installation will be done properly. Let us now show you that how you can take a case study and you can solve using this LAMMPS SPH multiphase. We will be showing you over here a drop on a solid surface, and due to contact angle how that is taking different shapes. Okay. So, we have named the case study as contact angle. So, case study is contact angle. So, what we can do, we can open a folder, okay, called contact angle, or if it is already there you can go in the SPH LAMMPS multiphase. So, it is already, this is a case study or already developed case study in LAMMPS SPH multiphase. So, therefrom we have taken, so it is already existing folder. If you are having some new case, you have to develop the folder and then you need to write down. So, the case study folder we have to go, which is nothing but home LAMMPS SPH multiphase, then surface tension _clean. There you can go to examples users SPH contact angle. Okay. So, this is the path of the directory where you need to go. In this path contact angle, in this folder contact angle, you can find out actually 5 files, okay, in which 2 files case 1 LMP and case 2 LMP, those are actually for basic informations, but you need to run this droplet LMP, set time LMP and run.sh, okay, for setting up the simulations. Okay. So, Let me explain one by one what all these files are dealing with. So, case 1 LMP and case 2 LMP, these are giving you the definition of obtuse and acute contact angles. Okay. So, we know that contact angle can be more than and less than 90 degree, depending on that we are having cases of obtuse and acute contact angles. Okay. I will be showing you details of one .lmp file. So, case 2 LMP I will be showing you, and I will be giving you how where this case 1 LMP is differing, rest comments will be same. Apart from that, I will be showing you the placement of this droplet.lmp, that means initial placement of the drop that is being specified in this file. For running the calculation, we need to set the time. So, set time dot lmp will be giving that one, and for running the informations are required in run.sh. Let us see quickly what is case 2 LMP. Important things I have highlighted over here. You see this part is given over here. See this Lx, Ly and Dx, these are actually your domain span in x direction, y direction, and Dx is actually your smallest size of the cell, okay, in which we will be placing the particles initially. Initially the particles are placed in a rectangular grid. So, that is the grid spacing. Okay. So, we have taken over here Lx by Nx. Nx is a predefined value which we give in the file while running. I will be showing you where the Nx value we give. Here similarly, we have given the density of the droplet. You see we are having two things over here. So, SPH rho d and SPH rho g. So, initially we have given those values as 1. Okay. Similarly, here we are having speed of sound, okay, SPH CD. So, C means speed of sound, because we have seen that speed of sound is very important, at least for von Neumann Richmer artificial viscosity. So, we have given those values as 10 10. Okay. Here we have given the viscosity of the droplet. You see the viscosity is written as eta. Okay. So, eta d and eta g. So, initially we have given those values as 5 into 10 to the power minus 2. Then if you go further, then you will be finding out in this position we have given the surface tension. As we know that to create the contact angle contact angle, we need to give 3 surface tensions, sigma SW, sigma LW and sigma LS. So, liquid gas, liquid wall and liquid solid wall. So, those values are written over here. So, alpha is actually your surface tension over here. So, alpha GD between gas and your droplet, here this is gas and wall, and here droplet and wall. Okay. So, these values are actually used in our Young's equation. We find out over there. Using this we can actually evaluate the value of the contact angle. Okay. Then here we have given the radius of the droplet. You see the cylindrical radius of the droplet we have given as 0.1875. Okay. Then here in this section what we have given the type of particles. So, we are having actually 3 different types of particles. First type of particle G type equals to 1 we have given for the gas, okay, around the droplet. Then D type equals to 2, that we have given for the droplets inside particles of the droplet, and then W type, the wall type particles we have given as 3. Okay. Now, this is more or less the file what we see in case of your case 2.lmp. Okay. Case 2.lmp is actually for acute contact angle. Okay. So, these combinations of alphas will be giving you acute contact angle. Okay. But if you see this case 1.lmp, these values are actually modified to 1, 1 and 1.5. See over here dW value is actually taking important role for deciding whether it is obtuse or acute. Next, let us see the droplet position. So, droplet.lmp. So, at the beginning here we have shown that how to set the dimension and the units. So, dimension is 2 and unit, it is not that much important in SPH lamps. We always use it as non-dimensional, but you have to give SI for the sake of completion of the code. Okay. Then over here you see in this we have specified the boundary conditions. So, boundary we have given as PPP, that means everywhere we are having the boundary as reflective boundary condition. Okay. The variables we have defined over here, okay, ndim, index and 2D. So, this decides that we are having 2-dimensional domain. Okay. And here you see we are including which case. Earlier I have shown you case 1 and case 2 dot LMP, so for obtuse and acute angle. So here I can select by giving the proper value of I case which obtuse or which one we will be taking, or either obtuse and acute, that we can decide over here. Now in this we have defined the domain. If you see here we have given first the Z limit, as it is a 2D problem. In the Z limit we have given a very small thickness, so which is nothing but starting from minus 1 into 10 to the power 3 to plus 1 into 10 to the power 3. Okay. And we have also selected a small domain for wall in the y direction and x direction. So you see over here Ly wall, I have actually extended the y portion little bit of 6 times of the dx. So dx is the small unit which I have already shown you. 6 times of that we have actually expanded the domain in y direction just to increase the domain. Similarly Lx wall is also similar, Lx plus 6 into dx. X center and y center, those are actually the center location of the drop. So there we have given 0.5 into Lx wall and 0.5 into Ly wall. Okay, Lx wall and Ly wall already we have defined. Then let us create a region with a box which is a 2-dimensional box starting from 0 to Lx wall, 0 to Ly wall, and in the z direction starting from NLZ to PLZ. As it is a 2-dimensional problem, though that width will be very small. Now here we have specified the gas particles. You see, first we have specified all the gas particles inside the domain. That means everywhere with a square box we have decided the Cartesian grids, or then in the grids at the center of the grid 0.5 and 0.5 we have actually placed a particle. Okay. So initially we are having a rectangular discretization of the particles. Then over here in this we have given the wall type, because at the wall the droplet is resting. So we have actually specified the wall. So first we have created a group which is for the flow direction. Okay. So first the flow direction means where the droplet and the gaseous phase is kept. Okay. Then what we have done, we have subtracted the boundary, okay, from the flow. So we have created a section which is actually the boundary section. Okay. So over the from the overall region, if we subtract our flow region, our flow region, then we will be getting the boundary. Okay. Then we have set the boundary, okay, set the boundary as a wall type. So W type we have given over here. Okay. Then we have given the force to these wall particles, which is nothing but 0, 0, 0. That means we have made the wall particles as non-moving particles. Okay. So because those particles cannot move. Now whenever we will be running the simulation, it will be writing down the value. So for writing the value over here, you see we are using dump command. Dump command is useful for writing the value, and we are writing all the values starting from ID of the particle, those are the I's, okay, or J's, and then type of the particle 1, 2 or 3 for the gas, liquid and wall respectively, X locations, Y location, Z location, their respective velocities, and this is your viscosity, color gradient, those things we write down. Okay. Then we will be showing you over here that how using dump command we can go for velocity dumping and for your values dumping in a separate file which can be read in some external software like VMD. Okay. So here this is the command for dump for all the particles X, Y and Z location we are writing. Okay. All the elements X, Y, Z location we are writing over here. Okay. Then here we have specified the droplet, because you see we have just created the center, we have not shown that droplet is having which type of particle. So here you see we have first shown that what is the droplet over here, starting having a cylinder, okay, at X center and Y low. Okay. Cylinder radius we have given as R droplet, okay, and then we have given that cylinder, inside the cylinder whatever particles we are having, that is as droplet type, okay, that means 2 type. Okay. Then here we are running the simulation with time step. So here we have calculated the time step. So time step is equals to your 0.5 divided by delta t. Okay. So in this way the time step delta t has been selected, and the code will be running further. Okay. And it will be running for n time. So number of time you can decide. Okay. Now this is the run file using which we can decide the numbers, okay, for running all those previous files. For example, you see NX121 is very important. This will be deciding that what will be the dx value in x, y and z directions. Okay. Then here you see the name of the data file where it will be writing the data file in which fashion, that we have given over here. I case equals to 2 will be deciding whether to choose the obtuse or acute file. Okay. So, I case was going in the LMP file, okay, from where we will be choosing that which one we need to take. Okay. Similarly, to create a folder where you will be storing the values, okay, the output files, that will be right here. Okay. So, make d minus p and then the name, okay, over here. Now, first what we need to do, we need to run the simulation. So, for running the simulation we need to go for the respective folder. So, this is the command using cd, we can go to the respective folder, the path is given over here, and then finally just a single command bash run.sh will be running our code. Okay. So, that means this will be running this run.sh file, which will be giving the values to the corresponding LMP files for running. Okay. So, this is the result for the case. So, here you can see we have started with a hemispherical droplet, and due to contact angle, okay, it has taken a flattened shape over here. So, if you change the values of the alphas, okay, in the LMP files, okay, then you will be finding out this is becoming more flattened depending on the contact angle. A close look of this one you can see over here. Okay. So, at the end of this lecture, we have elaborated the Lagrangian discretization of the constitutive equations of SPH. Mass, momentum and energy equations have been elaborated. Okay, using Lam's multiphase, we have shown you one case study where droplet has been taken a shape over the solid surface. Starting from installation, setting model parameters, running the case and analysis of results have been elaborated. Now, to test your understanding, we are having 3 questions. Basis of SPH lies in fixed reference, moving reference, non-orthogonal reference and variable time reference. Correct answer is moving reference, it is Lagrangian in nature. SPH discretizes governing equations in using kernel approximation, particle approximation, Taylor series approximation or all of the above. Already I have shown you kernel approximation and placement of particles. So, this is actually correct answer is both kernel approximation and particle approximation. Third question, particle-particle interaction becomes important inside a sphere of radius. 4 answers we are having: half of the domain length, viscous length scale, smoothing length and product of particle velocity and time scale. Okay. So, correct answer is obviously smoothing length. I have shown you a figure also in this respect. So, with this I end this lecture. Thank you.